talk about this. I will stress a little bit about formal approaches to software engineering, and I will explain a little bit what I mean formal approach. I have nothing against, so for the record, I have nothing against empirical software engineering, so I really enjoy their works, papers, and the conferences there everywhere. But still, I feel that probably for my background or whatever, I prefer like a formal approach. So we stress a little bit this kind of formal approach. Of course, for safety critical systems, and I am Angelo Gargantini, and this is Lugano, and this is the Palazzo Gargantini. There is a Palazzo Gargantini, so I found a picture of the Palazzo Gargantini. It's not mine, so.
Andiamo lì stasera.
Okay, well, there is a McDonald's. The credits for the work I'm doing I've done in these years. Our group in the University of Bergamo, it's me, Patrizia Scandura, I don't know if you know her, Patrizia Associate Professor, Claudio Menghi, you may know him,
I know.
Okay. And then there are also Silvia and Andrea, they are former students of mine. Now they have a position like researcher at EDA, the first step of the researcher. We have also Nicola Zeni. Nicola Zeni is from Trento. He works in the project Changes. We have a lot of PNR projects, so we have been recruiting for positions for a while. And we have also Nico, it's a new senior ricerca, ASMA as well. She works on digital twin and quantum. And Cesar is from Rio Quarto. You may know Nazareno Guerre from Rio Quarto. And he is from that group that I visited this summer. And together we also came up with this idea of a FOSE lab, formal. The idea is to put together formal methods and software engineering. It's a kind of laboratory. There is no physical laboratory, but still it's like a virtual entity of FOSE lab. And this is the outline of my talk. I will talk about a little bit about this formal method we are working on, and also something about testing. I won't go in details, just to give you an impression what we are doing in Bergamo. And first, we have our own set of tools, framework, and language, which is called Asmeta. It's based on Abacet machines. Abacet machines were invented by Yuri Gurevich. Now probably he's retired, but he used to work for Microsoft, and he came up with this idea of Abacet machines. Abacet machines are very simple. They are like in a state. You take like a screenshot, of your state, and this is an algebra, so it means domain, function, relations, predicates, and so on. And then you apply a set of rules to get a new state, and the transition is done atomically done. So you get from S0 to S1. You apply all the updates, and you get a new algebra, a new structure, and then you go again. You apply the rules. And to decide how to go from one state to another, there are like a program, pseudo program, which is I will introduce a little bit some ideas about this project. And around this Abacet machine, we have built our own tool, which is called Asmeta. We have also web pages and so on. We have also several tools during the years. So the tool itself is more like a collection of many tools. And what we do actually is that every year we introduce new techniques or new algorithm around this our own language. And we have like this will be the part regarding the design, the modeling. We have a tool like an editor, a simulator, compiler, and visualizer, so some visual stuff. And around this there is also part regarding verification, like we have a model checker which is based on USMV model checker, and also we have a language for writing scenarios validation. And this is part more like the first phases in which we want to design your system, you model your system, and then for the development there is code generator, like this one. There is also one we're working on in Java, and test generator or something like that. Everything is based on a meta model. This is the name comes from meta model because there is a meta model. So as meta means subset machine with meta modeling tools. Now it's somehow lost because it's buried down in the tools, but there is a meta model. There is this one that it's also based as the machine are based on the idea of refinement. So you start with a very abstract machine, then you add details until you get a sufficiently detailed model, and from that you generate the code, part of the code of your system. So there is no advantage to build the entire system using the abstract machine, but part of the system would be written in the Java code, and then you embed the Java code or C++ code in your system. And on this, you apply, for this chain of refinement, you apply a refinement. It's called stuttering refinement. Is a restricted form refinement. And here, instead, there are some verification validation tools like simulation, model checker, and so on. This is a screenshot of the tool. It's embedded in Eclipse, and this gives you like a taste of you can declare domains. It's more like a programming language, but very abstract, so you don't have all the details of the power of a programming language, but you have like domains, functions, variables or constants, and then you have rules like this one. Rules are very simple, so rules are just if something happens, then do something, apply an update. It's very, very, very simple. Rules. And the idea behind the semantics is that the rules are evaluated in the current state, and you collect all the updates, and then you apply all the update set at the same time. For example, here if you have like the assignment to x1, then comes 1, but you have like x equal x plus 1 and y is equal to x, you collect the updates. So for example, x will be updated to 1, but this x is not updated before the application, so this is still 0, so you have y is 0. Something like you collect all the updates and you apply. It's not like a programming language, and this is the parallel execution of all the rules. And okay, this gives you some abstract behavior of the program you write. You can write also scenarios. Let's see if I have like scenarios like a unit test for abstract specifications, and then you can write a scenario. Then you can write, and you can assert something like a check. You can set some variables, and then you can write. You can get also some information about the coverage. And this is an example of scenario. You have like you load the specification, you set, and you check something. And also, of course, we have also model checker, so we can add properties, LTL or CTL properties, and you can use the operators like G, X, and so on, the LTL operators. And this is actually translated to SMV, and then the verification is done in USMV.
It's done, sorry, you said?
In USMV. Not everything can be proven in USMV. We use, or sometimes we use also new XMV, which is more powerful. It's based on bounded model checking, but still doesn't work always. Sometimes it doesn't work. And of course, there are some limitations about the things you can. There are some limitations in terms of theory. So, for example, only defined domains and so on, but also in practice. So the system has not be. So our students tend to write a very big model, and then they try to prove some properties. It doesn't work because the model is too big. But still, so for that, we encourage the students to use also the scenarios, which are instead they work even in a more general settings. And what else? Of course, test generation will be the which is based also on model checker used for test generation. This is my old work on using logical solvers to generate tests. It's very classical thing. You use like a model checker to get a counterexample, and then use a counterexample to derive a test. From the model checker, you get a counterexample. This is very classical use of a model checker. And you get a test and also some coverage info. So you can say, okay, I cover enough this part or not, it depends. You continue with this. But at the end, we also, okay, this is very useful. You are very confident that your model is correct, everything is going well. But then at the end, you have the implementation on the other part here. So we also try to use these models or reuse these models also to check the conformance of real systems. So you have the implementation, and then you try to see if the implementation really conforms to the specification. This can be done in two ways. I won't go to details. One is offline, so you generate the test and then you run the test on the real system. Or the other one is at runtime. You connect your specification to your system, and then you runtime perform and check that the specification and the system produce the same behavior with all the problems you have, like non-determinism. We are working on this now. We're working for ABZ 2025. We're working on connecting a runtime specification to a artificial intelligence algorithm. So you have like your artificial intelligence or machine learning based system. Then you try to connect to. This is one of the case study of ABZ 2025. And so the idea is that to have like to put together artificial intelligence, an artificial intelligence based approach with a formal approach. This is the case I wanted also to mention the case study. Every year there is a case study. BZ, we apply these tools we have to these case studies. I also to mention I'm very proud of what we have done during the pandemic. It was during the pandemic Bergamo was was a center of we saw many elderly people die there, and there was a shortage of ventilators. So a friend of mine, Cristiano Galbiati, said, okay, we have to build our own ventilator. He's a physicist, he's not a computer scientist. And we have to build our own ventilator, which will be here. Of course, there is a software inside. It's very simple. The ventilator just there is a compressed air, and then you have like two valves, and you open and close the valves to inflate the lungs. So there is no, it's not, I mean, from the point of, it's not a big deal. But still, there are some constraints. For example, you have to limit the pressure, and you have to also to give the alternate the inspiration expiration, and this is all software controlled. And so what they did is they started with the prototype. At some point they realized that to be used, the software must be certified, of course, and the software was not good enough to be certified. So they called me and said, okay, please help us with the software. And what we did was software certification of this ventilator, and we didn't apply any formal model. I have to be honest. So there was no form. We had I don't know. It was a choice somehow, and so somehow I regret the choice. But we didn't have enough time. The people working in the international team were not expert in formal methods, so were hundreds, so it was difficult. But the good story was that at the end we were able to produce a ventilator. So we produced the ventilator. The company here also physically produced the ventilators. I don't know where they are now. I think they are in Africa, whatever. But we were able to also gain the certification, so it can be used in the hospital. I don't know, if I go to an hospital, see this ventilator, I will ask maybe, it's not the most powerful ventilator because it's very simple, very simple. It's from the medical point of view, keeps you on the basic. A couple of modes pressure and pressure control, the pressure support ventilation, but still it works very well, and the software was certified, so with the testing, with all necessary to be sure that we don't kill people with the ventilator. So I'm very confident that we haven't killed anyone with our ventilator. Okay, that's a good point. And also we have also published some paper on this about the experience from the software engineering perspective, not the formal methods. So this is the reason why last year we decided to also try to apply formal methods to this case study, because we didn't apply anything formal at the time. The other area I want to cover is combinatorial testing. This kind of thing, I like very much this combinatorial testing because it starts from very simple models. You take just the inputs. So, and we also have built some tools, but to give you just an idea of the inputs you start from, they are just parameters. And you say, okay, this is a Boolean, this can be a speed and integer, this can be a direction. And then you want to build a test suite that covers all the combination, or the pairwise combination, or the tree-wise, and so on. And although it's very simple, it's also very challenging to build a small test suite. So, and there is also competition, and we have done some work on this. We have built several tools using. I will say something about the last one. And in the last one, we tried to do we use SMT solver. It works in this way. We have the tuples that we want to generate. We try to do in parallel, and we use SMT solvers because the problem here is that normally there are also constraints. I didn't put constraints here, but normally there are constraints like, okay, during the night the speed must be less than 28, something like that. So there are constraints, and for these constraints we use these empty solvers. And typically, in my work, I try always to use solvers or logical solvers of several kinds to problem of software, like software testing or validation, verification, or analysis, whatever. And this is also interesting. One problem that I see in this kind of approach in which you use the model is the evolution of model. So, for example, this is an example of feature models. I also like very much, feature models are very, very simple. You have features, and then you have relation between features. These are optional, this is mandatory, then you can have OR, XOR, and whatever. And then you generate this. It's very similar to the combinatorial models. Then you generate a test suite. Test suites are products of your software product line. This will identify a software product line, and this will be a set of products for your software product line. And when the model evolves, because you may want to introduce new features or correct the relation among features or whatever. And the evolution, what happens to your test. And this is true for all the time when you use a model to generate the test, and then the model may be updated because you need to add something or correct some error, or even follow the changes in the requirements or whatever. And what happened to your test. And again, you may want to rebuild the test from scratch, or you may want to reuse some tests. And in this respect, we have done some works that I present here. For example, this one, we tried to see if we can build a test suite starting from an existing test suite. Some kind of repairing. You have a test suite, you change the model, but then you don't want to generate your test suite from scratch. You want to just take what you can, and you can rebuild the test suite. In this kind, instead we have evaluated the cost of the reusing. So because reusing sometimes is not the best practice, sometimes it's better that you throw all the tests away and then you start again. So it's a kind of trade-off. Of course, it depends on how much time you have, how much cost you want, because reusing has also some advantages in terms of other artifacts you have derived from your existing test suite. In the last one, we have also investigated the idea of targeting exactly model modification. So you have some edits of your model, and then you want to target exactly the modification of your model. And the last one to finish. It's we have we have done some work on testing neural network, because actually this was born because of a collaboration we had with the company, a small company. A student of us founded the company. I sent, now it's quite big, it's getting bigger and bigger, and they had like a very simple neural network for classifier and they wanted to test. So they came to us and said, okay, let's test this this network. And what we did is we introduced the idea of the idea of robustness. We have defined our own robustness in terms of alterations. This will be an alteration. This will be the original, and this will be alteration of the inputs. And what I'm very probably too fast, but just to give you an idea. I don't want to go too much in detail. When you alter the inputs, your accuracy of your network probably will decrease. So if you started with the original, I don't know, 95% of the accuracy, and then when you alter the inputs, you decrease the accuracy, because the network is no longer able to classify correctly the images. And what we did was we define so this will be the range of possible alterations, and this will be the subset in which the network still performs well. And so the larger is this A, the more robust is the network. So we define like a ratio between these two quantities.
And an example of alteration is like, I don't know, images are transmitted not in a lossy way, maybe, and you say, well, you cannot JPEG. Lose too much.
Exactly.
Okay.
So we had like something very typical of images, like brightness, contrast. Sometimes we use so it's necessary to have a little bit of knowledge of the domain. So for example, they say, okay, it was they use a LED. So say, okay, sometimes a LED changes the frequency, so the colors change. So it's not the brightness, but the color. Yeah. Or in another work we did with another student at Tenaris, they have a camera outside, and it was sometimes the sun was just in front of the camera, so we put like a sun in the camera, or sometimes there is just a row of pixels that are broken, or something like that. And also compression. Compression was also a problem. With the JPEG compression, we decided, okay, what if, for example, I want to transmit to a doctor I don't know, the scan of something that I will compress too much, and the doctor will apply, and then the machine learning will be wrong completely. The idea is, in that case, that because they had only, they were not completely confident of the image set, so the data set where they applied the training. So this will be a way to produce new data for training. But instead of, okay, you can retrain to like a data augmentation or something like that. But also you can also we applied also other stuff like doing like a parallel network, something like that. So, but gave the confidence that your network is robust or not. It would be very, very interesting. We have also done some work on this using Bayesian network with uncertainty. So we can also take into account uncertainty in the classification and say, okay, if I prefer a network that sometimes gives, I'm not sure that instead of a network it gives always some result, but is not confident. So robustness is also defined to keep it. This will be the last work we have done.
Angelo, I have a question. So in this work when you assess the robustness, how do you ensure that the input that you alter is still valid?
Yeah, no, there is no, there was I mean, we had some measure, like for the images you can have measures about the images. I don't know, you increase the brightness, but you still get a difference between. But it was domain specific. So the company said, okay, I want to decrease the brightness of this. And of course, we also define a way also to we introduce the probability of the alteration. Because sometimes also you want to weight some alteration because they are very improbable and likely, so you can like count less those alterations. That's very domain specific. We did also this also another case study in which we took from the standard benchmark like a German science or something like that, and also audio. So you can apply the same for audio inputs, so classification of audio inputs. Instead, this last work we have done with Wasim. Alessio knows the history of Wasim, and there was the uncertainty. This was and I hope that Cesar from Argentina will come and will work on this. So somehow now we are stopped on this topic. I hope to resume. Conclusion. So I think that I want also to discuss with you this idea of. I think that modeling. I already said. Where is the camera? There? I have nothing against empirical software engineers. Otherwise, they will. But still, I think that modeling is somehow part of. Also, as a teacher. I teach now software engineering in third year of the Laurea Triennale, and so I stress that engineers build things, but first they have models. So the idea of building models it's very important for not only for the part of validation, but also for building software systems. So I think we should stress a little bit more of the importance of models. And the models allow us to validate and verify theories. So it's like, you know, the falsification of scientific theories of Popper. So somehow that if you have models, if they are abstract enough, then you can apply something and reason about these models. And you have to allow people to reason about the models so they can, for example, UML is great. We teach UML, but what I miss in UML is the part regarding the validation. So UML you write, and then you don't know if it is even syntactically correct because maybe you use just a drawing tool. And the third thing is that from models, then you may want to derive some user stuff. For example, tests. So I also am involved very much on this idea of testing, also because I like that when you use models for deriving other stuff, other useful artifacts like tests or products or whatever. And also the other thing that is important in my work is that models can be learned. I don't work much on the models learning part, but can be repaired. So sometimes a model, you know that they are wrong, so you can start to think about how to improve or repair your models. And this is all. So thank you again for the invitation.